Hello, welcome to the second section of Chapter 5. We are in 5.3, so we're skipping over Section 2. So in this section, we're trying to solve for the general solution of differential equations. So like last section, we were just already given a solution of the differential equation and we were just told to verify whether it worked or not. So now, instead of just being given to us, we actually have to solve for it ourselves. So the method I want to focus on is called separation of variables. And this method is like what it sounds. We are trying to separate the variables. So let's do an example. Our differential equation is going to be y prime equals negative 6xy. Okay, so this is a differential equation because we have a mix of x's and y's and y primes all up in it. And so what we want to do in order to solve for a solution is to kind of split up our equation so that one side is all y's and one side is all x's. First, though, with this y prime, it's kind of hard to deal with because it is a derivative. So if you think back, way back in the day, we used to write derivatives in a multitude of ways. Another way that we could think of the derivative of y was dy dx. So instead of writing y prime, I can write it as dy dx. This is good because if I have dy over dx, I can kind of split this up by splitting it up into like one side being dy, the other side being dx. So what I want to do is I'm going to divide both sides by y. So I'm going to end up trying to move all my y's onto the left and all my x's onto the right. So by dividing by y, rather than doing dy over dx over y, I'm going to do 1 over y times dy dx. That way we don't have fractions on top of fractions. And then now I have y's on this side, x's on this side, except for this dx here. So I'm actually going to multiply both sides by dx. That way I end up with just 1 over y dy equals negative 6 dx. There. Now I have all y's on one side, all x's on the other. Also, this kind of looks like an integral now without the actual integral because we have like something dy, something dx. So to get rid of the dy and the dx, if I just integrate this, so I'm going to integrate both sides, that way we keep things balanced on the two sides, then the dy dx will go away. We just end up writing plus c. So let's integrate the two sides. On this side, 1 over y is technically y to the negative 1 power, but the derivative of what would give me 1 over y should be the natural log of the absolute value of y, plus c. On the other side, the derivative, or the integral of negative 6x is negative 6 times x squared over 2 plus c. Okay. I know I wrote plus c on both sides, because remember, when we take the integral of anything, there is a plus c there, but it's not necessarily the same number. Remember, c is that constant. We don't know what number it is. It could be any number, and they're not necessarily the same number. So what I want to do now in order to get my final answer is to solve for y. I need y on one side by itself, but by moving these c's together, I can't just subtract c on both sides and get rid of them. That's not a thing, because this number could be 10, this number could be 1 or whatever, and when I subtract, they don't necessarily cancel out. So keep that in mind. If you want, you could write it as c1 and c2 to remember that those aren't the same thing. You can't just get rid of it. But I am going to move the c1 over to the other side. That way I'm trying to get y by itself. This will end up being negative 3x squared. And then if I subtract c2 from c1, I end up with another constant. It's just a number, so I'm just going to leave it at c. Remember, c just stands for any number. We don't know what it is. It doesn't matter what it is as long as it's there. So remember, our goal is to get y by itself. So now I need to get rid of this natural log. What's the thing that's like opposite of a natural log. Hopefully you remember it's e. So I'm going to do e to the power of natural log y on this side, which means I need to raise e to the power of this stuff on this side. The e and the natural log will cancel out, leaving me with the natural log of y equals e to the power of negative 3x squared plus c. Okay? Getting rid of an absolute value is a little awkward. It just means whatever y is, the positive and the negative version would give me the same positive answer. So really, we're saying like both plus and minus of this would work for the absolute value of y. Okay, I just want to simplify this a little bit. Do you guys remember if I have an exponent that's being added by something, this is really just the same thing as like two things with exponents being multiplied, because like if I had x squared times x cubed, this is the same thing as x to the 2 plus 3 power. Okay, so you know, algebra 1 basics. So here, if I have e to the negative 3x squared plus c, this is the same thing as plus or minus e to the negative 3x squared power times e to the c power. Because if I were to multiply these together, their exponents would add, giving me negative 3x squared plus c. But the reason why I want to do this is because e to the c power is just a constant again, because c is just some number, e to whatever number is just a number. So that's another constant. So rather than writing it as e to the c, a more simple way to write this is just c. Also, c is a constant, so this plus or minus, whether c is a positive number or a negative number, doesn't matter. So telling us plus or minus c makes no difference. So my final answer is just going to be c times e to the negative 3x squared power. That is our general solution to our differential equation of y prime equals negative 6xy. And if I were to find the derivative of this, I would be able to get this by plugging it in. Okay, so that was one example of solving for the general solution using separation of variables. We're going to continue using this method throughout this chapter. So let's do another example. Okay, for my second example, I have the differential equation x squared plus 4 times y prime equals xy. So in general, every single time for each of these problems, you should be separating your variables, integrating, and then solving for y. So that's how we're going to do each of our problems. So first, I want to separate my variables for this. I'm also going to rewrite y prime as dy dx. Alright, so I've done a couple steps all in one go. So I rewrote the y prime, and then I divided by y to get it onto this side, and then divided by x squared plus 4 to get it onto this side. See how I have separated my y's and my x's? That's missing is the dx. I'm going to multiply it over to this side. That way I just have 1 over y dy equals x over x squared plus 4 dx. Okay, so I've separated all my variables. Now let's integrate. Okay, on the left with the y's, I have 1 over y times dy. Integrating that will give me the natural log of y, just like before, plus c. On this side, I have x over x squared plus 4. It's a little bit more complicated to integrate. I think we'll need to do u sub in order to integrate this. So I'm going to set u equal to x squared plus 4. Du would be 2x dx. Okay, so doing my u sub with u equals x squared plus 4, du would be 2x dx. Rewriting this, I need a 2 in order for my x dx to turn into du, so that's why I multiplied the outside by half. And then this, I end up being able to rewrite it as half, and then times the integral of 1 over u du. This ends up just being 1/2 natural log of u plus c. So then rewriting my u back in gives me that. Okay, so we're trying to get y by itself on one side, so let me subtract c on both sides. That leaves me with natural log of y equals 1/2 natural log of x squared plus 4 plus c. And then here, I need to get rid of my natural log in order to get y by itself. But I notice I also have a natural log on this side. So if I were to do e to the power of this stuff to cancel out that natural log, that probably would also cancel out the natural log that's on here, except for that 1/2 that's in front. So I can't have that there before I cancel out with the natural log. So I want to move it somewhere else, that 1/2. If you think back to our log properties, do you remember how if you had a number in front of the log, that was the same thing as having an exponent for whatever you were taking the log of? So I'm just going to rewrite this. So having the half in front is the same thing as raising whatever I'm taking the log of to the 1/2 power. That's also the same thing as just a square root. And if you notice, if we're taking the absolute value of x squared plus 4, that means this will always be positive, so squaring or square rooting x squared plus 4 should always be a positive number, which means we're allowed to take the square root of that. Okay, so we are ready to use e to the power of on both sides to cancel out the natural logs. That's kind of nice. Okay. From here, dang it, I done goofed. Okay, so backtrack a little bit. I can't cancel this out yet because I still have this plus c here. So this natural log was only applied to this square root. This plus c still doesn't quite cancel. So if I have e to the natural log of this stuff plus c, yes, the e and the natural log will cancel out, but this plus c here is still technically there. So I'm going to rewrite this like how we did in the last example. If you're adding in your exponent, that's the same as multiplying by e to the c power. So now I can cancel out e to the natural log, and e to the c power, again, is just another number. So this is just c times the square root of x squared plus 4 after canceling out the e and the natural log. Okay. And then because we have this absolute value here, that means this could be positive or negative, but because of c being like any number that's positive or negative, we don't need the absolute value anymore. We don't need the plus or minus. So our final answer is just going to be c times the square root of x squared plus 4. Okay, one last example, just for funsies. So this time my example has some trig in it. It actually makes this a little bit easier. So same thing, we're going to separate our variables, then we're going to integrate, and then solve for y. So if you want, pause it here, try it out. Let's see if you can at least separate your variables. Okay, by separating your variables, you should have gotten y dy equals secant x over cosine x dx, but secant x over cosine x is just secant squared x, because dividing by cosine, 1 over cosine is just secant. So that's how I got the secant squared x. Let's integrate both sides. On the left, y integrated would just be y squared over 2 plus c. On the right side, secant squared x is just tangent x. See, I told you the trig would make it nice and easy looking. So subtract c on both sides will give me y squared equals tangent x plus c still. And then I'm trying to get y by itself, so let me multiply both sides by 2. And then square root both sides to get rid of the square. Remember, when you square root both sides, you need the plus or minus. Okay, now that we have y by itself, that's our general solution to our differential equation. That's it for this section.